We are into chapter 20. I think it's 27. Let me double check. That's really bad. Completely forgot. Yeah, chapter 27. Ooh, I'm so smart. I can't believe I remembered that. Yay for me. Anyways, we're in chapter 27. That's the chapter on magnetism. I want to remind you, folks, what y'all were able to see in the Faraday lab. So, in the Faraday lab, we had various setups, but a good thing about that Faraday lab is it allowed you to actually see physically how the magnetic field was oriented around current carrying wires. And for instance, there was a long wire that went through a plexiglass plate, and then that wire could be set up such that it's carrying current either up or down, but straight perpendicular to that plate. And then we laid out compasses around the wire at sort of more or less the same distance away from the wire at each point. So it's sort of like in a circle around the wire. And then when we turn that current on, all the compasses oriented themselves so that they formed a circle going around the actual wire. And that showed you that basically the line of a constant magnetic field was a fixed distance away, r, from the wire, and that distance r was measured perpendicularly to the wire, and the current was, of course, perpendicular to that plane as well, and that in fact it was given by a right hand rule, such that if you take your right thumb and you take your right hand and you imagine grabbing the wire as if this were the wire, we would grab it with our thumb pointing in the direction of the current and let our fingers curl around it like that. And the whole purpose of doing that was that we'd see in which direction the actual magnetic field would orient itself. So the right hand rule with the current going up told us that if we looked from above the wire downward, we would see the current coming straight towards our skull, and we would see the magnetic field going in a counterclockwise direction around that, such that the magnetic field would literally be a constant on any circle centered on that wire as long as that circle was perpendicular to the wire itself. So I've drawn this as well in a diagram on my iPad, and I'm going to show that to you, but I wanted to make sure we had some understanding of that scenario and remind you that you had that option to see it on the actual Faraday lab. So another idea you can use for that, just to get an idea, is I just take anything circular. I grab this green duct tape, and in fact, I was noticing that we can even tell this green duct tape is actually wrapped around. You can see the duct tape is wrapped around in this way. Okay, so you see the duct tape's wrapped around in this way, which from that perspective is counterclockwise. Similarly, when I take my right thumb and stick it up, my fingers curl around in that same counterclockwise way that you see here. So what you can do to picture what the magnetic field like a around a current is you can imagine the current coming out of the circle. So we're going to put this pin representing the wire, and we're going to put it perpendicular to the circle, dead center in the circle, and we're going to imagine the current going up. So maybe it'd be better to point it that way because we know that the point of the pin is that way. If we did that, then this would actually dictate on what line is a constant magnetic field. Well, the line is this line of constant radius from the wire. And in fact, right here, it would point this way. Right here, it would point this way. Right here, it would point this way. And right here, it would point that way, all while the current is in that direction, which my hand's all in the way. But that's another way of looking at it. So it's good to think as many ways as possible so that you can get a better feel for 3 dimensions, what this right hand rule is, and that sort of thing. So with that in mind, let me go ahead and jump to chapter 30 and to my iPad by sharing that screen. And you'll see that in a second. So I've already taken the time to sort of draw a diagram of what we had set up in that lab. And you see here that we have the current carrying wire and the current is in fact going in the upward position, the upward direction, which is what I call the z-axis. The way I've drawn this, I have the x-axis pointing to the right, I have the y-axis pointing into the page, and I have the z-axis on the page but pointing up. So that they're all mutually perpendicular. And now I've drawn a purple circle of constant radius r from the wire, and then I've chosen four specific spots to draw where the magnetic field uh, line, or to draw a magnetic field line showing its direction and approximate its magnitude. I tried to draw all these arrows the exact same length, but there's really not a clean way of doing that in this program that I'm using. So I just sort of added, if you will. But since they're all a fixed distance away, r, then every one of these vectors should all have the exact same magnitude, so they're all the same length. But you should also realize that I'm using perspective here so that you see the right edge of this plexiglass table is at that angle, and that's approximately the same angle that I put for the magnetic field here. Similarly, the left edge of the plexiglass table is parallel to this magnetic field coming out approximately. Uh, I'm using perspective there, and in principle, it should be slightly different from this angle. And this one, they shouldn't be exactly parallel, but really close. And the same thing here, they shouldn't be exactly parallel, but really close. But the ones going left and right certainly are parallel to the back. So you see the magnetic field behind the wire is pointing to our left, and the magnetic field in front of the wire is pointing to our right. And in fact, you could even draw in between and realize that right here, the magnetic field would be that way. Right here, the magnetic field would be that way. Right here, the magnetic field would be that way. And right here, the magnetic field would be that way. So everywhere along that circle, if you draw a tangent vector to it, such that the tangent vector points in the counterclockwise direction as seen from above the wire, then you'd have a valid magnetic field vector. So that's what these B's are, is a magnetic field vector. And what we learned in the uh, Faraday lab was that the magnetic field was proportional to the current and was inversely proportional to the distance from the current carrying wire to the point at which we wish to measure the magnetic field. And this is the actual result of that. We will derive this later with a law called the law of Biot-Savart, but right now we just need to know that that is the formula for a magnetic field caused by a current I at a distance r away, and the theta hat is an actual unit vector that I'm getting ready to show you with the diagram below that to show you what it is. Because we're just going to use these over and over again because it's a real succinct way, for one, to get you guys started thinking about different coordinate systems, but two, to get you guys understanding exactly what directions we're talking about. So theta hat is a unit vector that points in the direction of increasing theta. R hat is a unit vector that points in the direction of increasing r, and rho hat is a unit vector that points in the direction of increasing rho, which is the same thing as r, except this r in general, when we use r, that could mean a three-dimensional r, which would be x squared plus y squared plus z squared. Take the square root of all that, that would be the distance away from the origin, and that would be the r that we talk about in spherical coordinates. But if you talked about the r that we talk about in cylindrical coordinates, then we would refrain from using that z-axis, and we would only talk about the square root of x squared plus y squared. So sometimes different books will call that coordinate in two dimensions, they'll call that rho, and in three dimensions, they'll call it r. So I often will call it r cylindrical, r with a subscript CYL, or I will use rho. So I just want to get you ready for that. But now that we have that, I also need to explain what the other constants are. Obviously, the 2 pi you recognize, and I want you to realize that the electric field, due to a infinitely long uniformly charged wire, if you remember correctly, that electric field was E is equal to lambda, the charge per unit length, divided by 2 pi epsilon naught r, and it actually pointed in what we would call, in this case, I would call it r cylindrical hat, r lambda over 2 pi epsilon naught r times rho hat. Either one of those are acceptable, but I wanted you to see how similar it was in form to the magnetic field, even though the directions are perpendicular to each other. The formula is essentially the same. It even has a 2 pi in the bottom. It's inversely proportional to the distance, just like the electric field is, and so on. It does have a constant, of course, the epsilon zero that we use from Gauss's law is 8.854 times 10 to the negative 12th coulombs squared per Newton meter squared. In this case, we have a constant mu zero that's called the permeability of free space, or specifically, it's the permeability of a vacuum, and that's 4 pi times 10 to the negative seventh Teslas times meters per amp. So that's what this quantity is. I'm going to write this word down so you'll know what we're saying. It's the permeability of the vacuum. So the subscript O, just like it meant in epsilon zero, the subscript O or zero, whatever you want to call that, is indicating that this is as measured in a vacuum. And it's, you can imagine in air it's slightly different. Like, for instance, I think we discovered that epsilon for air was 1.0006, if I remember, times epsilon zero. So it's really not that different. It's just a difference of six in a fourth decimal place. Probably the mu for air is differing by no more than about a sixth or a decimal of six on the fourth or fifth decimal place as well. I don't know that one off the top of my head. I just didn't look it up, but they're pretty close. So, anyways, that's the permeability of free space. That's how the magnetic field works for a current carrying wire, and that's a right hand rule that you want to use. The right hand rules are almost always in the form of something like this, where you take your hand and then you imagine curling it, or you take your hand and you point your index finger perpendicular to your thumb, and then you point your middle finger perpendicular to your thumb as well, but maybe even perpendicular to your index finger. But that's only in the special cases in which this and this are perpendicular to each other. They don't always have to be. What we do know is when we're using the right hand rule to find, for instance, a direction of a cross product, which is how this form's often used, is that if these two are perpendicular, this would be the A vector and this would be the B vector in A cross B. And then the answer to that A cross B would be the direction of this thumb, which is mutually perpendicular to both. But when you go to use it that way in terms of a cross product, this middle finger can be any angle but zero and any angle but 180. So if it's 180 where it's turned completely backwards, you get zero for the cross product. If it's 0 degrees where it's parallel to the index finger, you get zero for the cross product as well. So all of these angles with the middle finger work fine. It's just when you get to straight up parallel to the index finger or straight back anti-parallel to the index finger, then that cross product becomes zero. So keep that in mind. Now, just to give you an idea exactly what the theta hat vector is and the r hat vector that we're using here, this r, like I said, is what I'd call r cylindrical, r polar, or just plain rho. Okay, so r cylindrical, r polar, because you guys have probably heard of polar coordinates at least. I hope you have from pre-calculus and trig. But either way, that's the two-dimensional non-z component of a radial vector in some sense. So what are the actual unit vectors? Well, one unit vector continues on that straight line parallel to the line from the origin to the point, and that vector is the r hat vector. And I tried to draw that perfectly straight. I mean perfectly parallel to the green line, and I'm sure it's not, but that's my attempt. This is the r hat vector, which is also what I called r cylindrical hat vector, which is also what I called rho hat vector. Okay, and you can see that since it's parallel to the green line, then clearly this angle between it and horizontal is also theta. Okay, so that tells us, for instance, that the if you imagine x and y components, you could see that the x component would be right here, and the y component would be right here, and the x component is equal to r, the magnitude of the r hat vector, which is just 1 times cosine theta, and the y component is just 1, the magnitude of the r hat vector, times the sine of theta. So we immediately realize that r hat, which equals r cylindrical hat, which equals rho hat, all of that is equal to cosine theta I hat plus sine theta j hat. In addition to that, there is 90 degrees ahead of it another vector, and that vector points in the direction of increasing theta, and that vector is called theta hat. Again, we can use the geometry of the situation and realize that this red line was parallel to the x-axis and this red line is parallel to the y-axis. And we also see that this angle right here is also theta. So we can see, for instance, that this would be the y component of theta hat and this would be the x component of theta hat. So the x component of theta hat should be equal to, notice, even though we're in the first quadrant, it has a negative x component. So that x component is going to be negative sine theta, and that y component of theta hat, that's actually positive, but that's going to be cosine theta. Remember, it's times 1 because the magnitude of the theta hat vector is just 1, but I just left it off here because I did take the time to show it on the last slide, or excuse me, on the last calculation. So now I also know that theta hat is actually equal to negative sine theta I hat plus cosine theta j hat, and it's not a coincidence that dr hat over d theta is actually equal to theta hat. So that's another way that you can remember what theta hat is, by just figuring out what r hat is and then taking the derivative of it with respect to theta. So those vectors come in handy. And just to give you an idea, if you're talking about this position, this point in space, for instance, now you draw a line from here to the origin, and that tells you that r hat would point that way and theta hat would point that way. And you can see that if this is the point in question, then theta hat is going to point this way, and r hat is going to point this way. So you can see, as the position in space that you're talking about moves, the r hat and the theta hat move as well. You can see, in fact, in that last point, that the r hat became equivalent to the negative I hat, and the theta hat became equivalent to the negative j hat. You could also, of course, take a point right down here, in which case you'd find that r hat is that way and theta hat is that way. So hopefully, by me covering all that, it should be obvious to you that the theta hat is the variable that we want to use when we try to represent the magnitude or the direction of the magnetic field around a current carrying wire that happens to have it happens to be lying along the z-axis with its current going in the positive z direction. So hopefully that'll come in handy to you guys. The other thing I need you to realize is that there's very specific magnetic forces that result from a magnetic field. So for instance, if you have a charged particle moving in a magnetic field, then you have a force given by This is a magnetic force, so I'll put a subscript B on it because we use the symbol B to represent magnetic fields. Some books use H and stuff like that. Just be advised, they're not always talking about the exact same thing. So, for instance, sometimes what people call as a magnetic field doesn't have the units of Tesla. Sometimes the magnetic field that they talk about has units of Webers and stuff like that. So you got to be careful when you're reading the literature about electricity and magnetism. Not everybody agrees on the wording of what the magnetic field is versus other things. So just keep that in mind. Uh, I'm going to go ahead and make sure this chat's open because last night I was teaching and right in the middle of it, the computer froze and I just thought it was my image that was changing, not changing, but it turned out that for my viewers, the actual iPad screen wasn't changing either. So I want to you guys holler and let me know if that happens because I don't know how long I went before this. Before I figured it out myself, but my students didn't tell me. So, anyways, the force due to a magnetic field acting on a particle of charge q with velocity v is q v cross B. Okay, so you see that's a cross product, and remember I told you the right hand rule of the cross product. This index finger represents the first vector in the cross product, so that would be the vector QV in this case. So if Q is a positive charge, then QV is just parallel to the velocity. But if Q is a negative charge, then it's opposite to the velocity. And then the second vector in this case would be the magnetic field, which would be this index finger. And you'd like them to be perpendicular because then the math is really straightforward and easy. But they could be, in actuality, they can always go all the way to 0 degrees and even all the way to 180. It's just at 0 degrees and 180 degrees, it's going to come out to be zero. But if it's not 0 or 180, then it'll come out to be different from zero. And in fact, the direction will be given by your right thumb. So that's the direction of the cross product of this vector and this vector, where this vector right here need not be perpendicular to the index finger. Strictly speaking, it could be as close as even parallel, but like I said, parallel and anti-parallel gives you zero. So that's the orientation, or that's the magnitude of the force acting on a charge q with velocity v in a magnetic field B. You also have a magnetic field causing a force on a current carrying wire. And in this case, I like to talk about it in differential notation so that we'd say a small little bit of force dF is equal to I times the itty bitty vector dl cross B. Part of the reason why I bring this up now is I want you to notice that the units of IDL is amperes for I and meters for DL. So we get ampere meters per second for IDL, whereas when we look at QV, we get coulombs and then we get meters per second for V, but a coulomb per second is an ampere, so they're actually the same unit. So that's why the QV and the IDL sort of play the same role. Now, it's very important that you be able to apply this right hand rule. So let me do a couple of examples. Let's talk about a positive charge right here. And let's imagine that the positive charge has a velocity this way, and we have a magnetic field that points into the page. So, with that in mind, can anybody tell me which direction the force is? So F sub B. Y'all can type it, you can state it. What we can do just to help it make it easier for you guys to state a direction, we're going to call this the X direction. We're going to call into the page the Y direction, and we're going to call on the page, parallel to the page, the Z direction and upward. So your directions could be positive X direction, negative X direction, positive Y direction, negative Y direction, positive Z direction, negative Z direction. Does anyone have a direction for FB? If you don't worry. I've given you, someone said upwards positive. I've given you the right hand rule. Now I'm going to show you how to use the right hand rule. So looking at this, what I'm going to do is first off, I notice that the charge is positive. So QV and V are parallel. That means my index finger is pointing to the right. The magnetic field goes into the page, but until I figure out where that magnetic field is, I can hold my hand like this in any of these orientations, and it doesn't matter because I haven't nailed down exactly what the magnetic field direction is. But once I have the magnetic field direction, then I got to turn my hand such that my middle finger can turn towards it. So in this case, the middle finger should point towards into the page. That means my middle finger goes like this. There you go. Just like that. And you see that my force is the direction of my right thumb, which points straight up. So QV cross B is in the positive Z direction. That's important to know. That's something you've got to be able to understand. So make sure you guys work that out. Now let's try another one. Let's try a negative charge. This time the negative charge is going to be moving to the right. Again, we're going to use the same axes, but this time I'm going to say the magnetic field is up. So B is up and V is to the right. Again, this is the positive X direction. Into the page is the positive Y direction. And upwards on the page is the Z direction. So, can anybody tell me in which direction is the force for this one? Okay, someone said positive Y. We'll check on this. What we want to do is, again, in this case, I'm checking the charge. The charge is negative. That means QV is in the opposite direction of the velocity. The velocity is to the right, so QV is to the left. That means all of these orientations are acceptable until I figure out which direction the magnetic field is. Well, the magnetic field in this case happens to be up, so I have to do that. And what I see is my thumb is now pointing towards away from me, which is into the board, and that means the positive Y direction. So this one says positive Y direction. Okay. Now, this is a current carrying wire up. Okay, the current is going in the upward direction. I want you guys to tell me what direction is the magnetic field right here in front of the wire. I'm going to point in the correct direction, and then you guys should basically have reached the same conclusion as the direction I point. But again, you want to use your right hand, and the way this right hand rule works is this right hand rule requires us to point our thumb in the direction of the current and then wrap our fingers around the wire in the direction that they naturally wrap because, our species doesn't allow our fingers to go back the other way, right? So when you have that, then that gives you the circle that you should imagine that is perpendicular to the wire and is around the wire. And in fact, the center of that circle should be where the wire intersects with that circular plane. So now that you know that, can everybody guess what direction the magnetic field due to this current carrying wire where the current is in the up direction, what direction is the magnetic field right here in front of the wire between you and the wire, in other words? This one just requires a direction like left, right, into the screen, out of the screen, up or down, something like that. Well, again, right hand rule says like this, so that means it's the magnetic field should be going around this way. And that means if I stop right here, tangent to that circle that we had just imagined is this direction. So that is the direction of the magnetic field in front of the wire. In other words, between the wire and you. Now, between the wire and me, the magnetic field should point this way. Which direction should the magnetic field be right here to my right of the wire? Yeah, that one's towards you guys. And over here to my left of the wire, it should be towards me. Good job. Good job, Nathaniel and Miles. It looks like most of you guys are getting this as well as Alex. I haven't seen Anahi, but I'm not sure if she's not getting it or if she's not just participating. But the main thing is you just need to do this. So like every time that you see a figure in this book in chapter 27 or 28, and it has a magnetic field and a charged particle with a velocity that's not zero, I want you to immediately cover up that diagram, picture the diagram in your head, and figure out what direction the force is. And then check to make sure you're right. If you see instead a current carrying wire, then I want you to think immediately what direction is the magnetic field at various points and then do that. Or if you see a current carrying wire in a magnetic field, then I want you to immediately figure out what direction is the force on that wire because it's the same formula, only in place of QV, you put IDL. DL is a differential length of line that happens to point in the same direction as the current. Okay. So there's no instant in which you point in the opposite direction like we do when the charge is negative. In the IDL case, the IDL always points in the direction of the current, and then the B points in the direction of the magnetic field, and then your right thumb gives the direction of the force. So every time you see a diagram where you can work out what the direction of the magnetic field is or what the direction of the force due to the magnetic field is, I want you to do that before the book figures tells you it. In other words, as soon as you see it, cover up the diagram and then slowly move your hand away so that you can see the diagram without it giving you the answer. Work out what the right direction is for that force, or if it's a different type of diagram, you might just be working out the direction for the magnetic field. That's okay too. But the main thing is, I want you to work out both of those so that you can use this right hand rule for figuring out the direction of the magnetic field near a current carrying wire, and this right hand rule where you figure out the direction of the force acting on a particle of charge Q with velocity V, or the force acting on a wire of current I whose length is dl. Okay. So just do that as part of the practice. I'm not going over the typical introductory stuff, and I'm not going over some of the more conceptual stuff. You guys just need to read that from the book. But I will tell you that we got the whole idea of using the word magnetism because it was first discovered in what's modern day Turkey, what they call Asia Minor, and it's a place called Magnesia. And there they found rocks that would actually sort of magically move. You could take two of these rocks, and if you put them too close to each other, they would actually collect ram into each other. If you put them too close to each other, sometimes they would run apart, and that was like they had their own volition, their own ability to move. So it seemed a little magical to them, but that was what we coined magnetism, and that's where we got the word magnetism from. Ultimately, there turns out to be three types. There's paramagnetism, ferromagnetism, and diamagnetism. Ferro, Ferro, as you might tell, that's the Fe, like we use for the chemical symbol of iron. That is the type of magnetism that iron has, and a few other things. But specifically, when you put a ferromagnetic material in a magnetic field, the magnetism of the individual neighborhoods of atoms tend to all align parallel to that existing magnetic field. And when you then take that iron out of that existing magnetic field, the magnetic field in that iron stays. If, on the other hand, you're talking about paramagnetism with a P, P-A-R-A, The same thing happens if you take a paramagnetic material and you submerge it in a magnetic field, then the individual atoms or individual neighborhoods of atoms will all align their magnetic field parallel to the existing magnetic field. However, when you take a paramagnetic material out of the magnetic field, the paramagnetism disappears. In other words, the magnetic fields of the individual atoms and neighborhoods of atoms, they just all fall back at random. Okay. And then finally, diamagnetism is a weird scenario where if you put a diamagnetic material in a magnetic field, the individual magnetic fields of the atoms or neighborhoods of atoms will actually align themselves anti-parallel to the magnetic field. But just like paramagnetism, once you take it out of the magnetic field, they just go back to random. So that's pretty much all the big concepts I'm going to be talking about here is as the normal conceptual reading stuff goes. So just make sure you read the rest. I think I've given you a pretty good introduction to not only the magnetic field equation for the strength of a magnetic field around a current carrying wire. I've also given you an intro to what R hat cylindrical is and theta hat cylindrical is, which is what we're going to be using occasionally. And I've given you the two forces F equals QV cross B and DF equals IDL cross B. Those are the force equations that we'll use, well, pretty much the rest of the semester. And you need to know these quantities here that I'm boxing off and these equations. So this one you don't necessarily need to know. Very it's not that common to have a PHY 241 or 242 class getting much exposure to cylindrical or spherical coordinates, but I've found that this works pretty well for my students, so I continue to do it. I don't make them go into details. There's a lot of cool details and stuff you can calculate with regards to these different coordinate systems. I don't try to make my students do that. I just want them to know that those hat vectors exist and that they're really convenient to use when you're talking about trying to specify the direction of a vector. So now that we have all that, I'm going to go on. I will let you know the sections of this chapter. 27.1 is magnets and magnetic fields. 27.2 electric currents produce magnetic fields. 27.3 force on electric current in a magnetic field. The definition of B, the magnetic field. 27.4 force on electric charge moving in a magnetic field. 27.5 torque on a current loop, magnetic dipole moment. 27.6 applications, motors, loudspeakers, galvanometers. 27.6 application, or excuse me, 27.7 discovery and properties of the electron. 27.8 the Hall effect, and 27.9 the mass spectrometer. Really, the applications and the Hall effect are pretty much things that I'm going to introduce. Well, I'm not even going to introduce the applications. I want you to read those for your own enlightenment, and it's very interesting. And I've even mentioned to you how you could make a galvanometer before, so we've handled that a little bit. But the Hall effect, I'm going to introduce just so you'll understand it, but I'm not going to require you to do any examples with the Hall electric field or the Hall magnetic field. I just want you to understand that basically when you run a current carrying wire through a magnetic field that's perpendicular to the wire, a charge develops or a voltage develops on different ends of the diameter of that wire. And depending on the polarity of that voltage, meaning whether the top is high voltage and the bottom's low voltage, or the front is high voltage and the back is low voltage, or vice versa in each of those cases, that allows us to figure out whether it's positive charge carriers that carry current or if it's negative charge carriers going the opposite way. And in fact, that's how we know that the charge carriers in current are negative, even though we use conventional current, which pretends like little positive charges are going everywhere. So that's me telling you that you're not responsible for any examples in 27.8 or 27.6. And I can imagine not 27.7 either, but the mass spectrometer and the other device, which is called a velocity selector, those are rudimentary fundamental physics that you should be able to know how to calculate the radius of the arc that a particle will get when it's traveling in a magnetic field and stuff like that. So when we get there, you will need to know those. Let's move on to some examples now. As I said, your book gives you quite a bit of introduction. What I want you to remember about the magnetic field is a couple things. One thing is this: magnetic field, magnetic fields are, and this is a little mnemonic I use, are like old people. They leave the north and that was a really bad H. Sorry, OCD won't let me leave it. No, and enter the South. So, how many times have you heard about elderly people moving to Florida? In fact, I myself could consider moving to Florida as I get older. But that's what I mean by this. So, if you imagine, for instance, a bar magnet like this one, you can say this is a bar magnet and it has a north end and a south end. And as the book tells you, if you were to cut this magnet in half, you're not going to get a north pole of a magnet that you can carry around and then a south pole of a magnet that you're going to carry around. Rather, what's going to happen when you cut it in half is now you have two magnets, each of which have a north pole and a south pole. And we've never been able to find an isolated north pole or south pole. That's called a magnetic monopole. And as far as we know, they don't exist. And one of the fundamental equations that we're studying in this semester, called Maxwell's equation, is an equation that more or less states no magnetic monopoles exist. But back to this mnemonic, magnetic fields are like old people. They leave the north and enter the south. What I mean by that is the magnetic field lines, for starters, never end. So they're pretty much, if you find them coming to an end, that's a transitory state where they're going to correct that in the near future. But like for a bar magnet, the magnetic field makes complete loops and goes completely through the magnet. So what this line means is, notice the magnetic field is leaving the north, and if we looked at it from this side, we would see it entering the south like that. If we considered a little bit off the center of the magnet, say over here at this edge, what we'd see is that this magnetic field starts to bend this way. And again, you can see that the magnetic field is leaving the north and then comes back around and enters the south like that. And the same thing here. I'm going to go right through here like this. So that's what magnetic field lines are like. And as you can see in the diagram, it has fuller diagrams where you can see the complete loop go all the way around. But I wanted to point out to you that the magnetic field lines exit the north pole of the magnet and enter the south pole of the magnet. Another thing I want to point out to you is that the Earth has a magnetic field, and that the Earth's magnetic field has a north pole and a south pole. And the north pole of the Earth's magnetic field is not, technically speaking, right at the north celestial pole. It's sort of in the Hudson Bay area of Canada, and it moves on the order of kilometers. I think on the order of a kilometer a year, somewhere around there. Your book tells you a little bit, but it does move. So, because of that, one thing you know is that the draw this a little better. I need to do a different color. Uh, the compass can give you a very bad direction if you happen to be, for instance, between the north pole of the Earth, the north magnetic pole of the Earth, and the north pole of the Earth itself, because it would tell you that the northern direction is due south of you. So what I'm picturing here is, this is the bar magnet that you can sort of pretend is what's causing the Earth's magnetic field. And what we know is that a compass, which has a needle that points to the north, that compass points towards the North Pole of the Earth, which means the North magnetic pole of the Earth is technically a South Pole. So that's the other thing I wanted you to understand is that the north magnetic pole of the Earth is one not at the north pole of the Earth. It's actually a little bit further south of that. So it's really convenient that we can use magnetism and therefore compasses to find north and south, but we've got to correct for that if we're in regions where that makes a big difference. You can see, for instance, in your book, they have a little map and they even show you what the direction magnetic north is versus the direction of true north, and you can always correct that while you're on the map. So that's why you have good maps as opposed to just crappy road maps, which are not good for camping. There's specific maps that you use for camping, and you should stick to those if you're doing camping. The other thing that that tells you, of course, is that the magnetic fields of the Earth are lines like this. They come out of the North Pole and loop back around and come into the South Pole of the magnet, which means the magnetic field lines around the Earth have this orientation, i.e., this uh, direction. And this line, of course, goes all the way through like that. And then you have another one coming this way as well. And another thing we'll tell you is that the units for the magnetic field that we use are the Tesla, which is abbreviated capital T, but it's also, there's one called the Gauss, which is capital G, and 1 Tesla is equal to 10 to the fourth Gauss, and the Earth's magnetic field, B Earth, is approximately zero point 0.5 Gauss. So that's sort of the information you need to understand about magnetic field lines, magnets. The Earth acting as a bar magnet is inside of it that rotates with it and stuff of that sort. The magnitude of that magnetic field is about half a Gauss. The typical magnitude of, for instance, an MRI device that you might use to have, a joint checked out or something like that is on the order of a whole Tesla. So zero point 0.9, 1.2, something like that. But we can even make stronger magnetic fields, 5, 10 Tesla, stuff like that as well. But generally speaking, the magnetic field that we use for a MRI is on the order of a Tesla. So now with that being said, we can move on to some more fundamental examples. All this stuff is explained in your book. If you wanted to make a uniform magnetic field, we found out how to make a uniform electric field. We take a positively charged plate, infinitely large. That's going to make a number of electric field lines that are perpendicular to that plate. And if you get near the edges, which would mean it's not infinite, but if you get near the edges, then that magnetic field starts to deviate away from perpendicular to the plate. So we just make sure we stay near the center. And then we take another plate with a charge on it, only this time the charge will be negative, and we put it right up against it as close as possible, and that makes a really uniform electric field. Well, guess what? If you want to make a really uniform magnetic field, you're going to imagine one end of this Rubik's Cube is a north pole of a magnet, and one end of this Rubik's Cube is a south pole of a magnet, and you put them really, really close to each other like this. That little space in there would make a very intense uniform magnetic field, and that's how we make uniform magnetic fields. And your book takes the time to explain that. And if you'll notice, if you look at figure 27.7, you see that on top they have a north pole of a magnet, on the bottom they have a south pole of a magnet, and they have the blue magnetic field lines pointing down. Because as I told you, magnetic field lines are like old people, they leave the north and enter the south. Any questions on that? Okay. Another question, just really quickly. If you imagine a current carrying wire here, let's say the current is coming out, so I'm going to draw that with a circle with a dot in the middle. And the magnetic field, or the wire here, has a current going into the page, and then the magnetic field here has a current going into the page, and then the magnetic field here has a current going out of the page. So for starters, I'm putting a red one around that so we'll know exactly which direction the magnetic field points for that one. I'll draw that one in a red color. So right here, can anybody tell me if that wire that's in red there, if that is actually a current carrying wire with the current coming out of the page at that black dot that I just drew, what is the direction of the magnetic field due to that one wire? Can anybody tell me that one? The answers that you can select from are up, down, up and to the right, up and to the left, down and to the left, down and to the right, out of the page, and in the page. So again, we're talking that top left current carrying wire that's supposed to be pictured to be perpendicular to the paper or to the iPad, and the current is coming out of the page, shooting me like in my forehead, say, and I'm asking you what direction is the magnetic field at the black dot. Can anybody tell me what that is? I'm getting ready to give it to you, but y'all should know it by now. Should be able to figure it out by now. Not just right, but that's halfway there. So remember, you got to imagine a circle around it. That's supposed to be a circle around that wire. And then use your right hand, putting your thumb sticking out of the page, and then your fingers curl around that in the correct direction. So right here, the magnetic field due to that wire should point up and to the right. Now, can somebody tell me what direction the magnetic field due to that bottom left current carrying wire is? Notice I drew that one purple, so I'm going to do this one in purple as well. So I'll use a purple vector to represent the magnetic field due to that one. Someone says southeast, and that's actually correct. So this vector would point this way. All right, now let's see this one right here. I just circled that bottom right wire with a green circle. So what direction is the magnetic field due to that current carrying wire, the green one? So remember to draw a circle around the wire where the wire is the center of the circle, and then use your right hand uh, to wrap your curl your fingers around that circle with your thumb pointing in the direction of the current. And Miles said southwest, and he is right on the money, which would be this way. Okay. And then finally, this blue one, the top right. This again, I just want to give you guys another chance to make sure y'all can figure out the directions of magnetic fields at various points around the current carrying wire. So with that blue one, what direction is the magnetic field in the center of that square? Someone said northeast. That's almost right. The red one is northeast. This one's more northwest. So that should be the direction of that one. Okay, so there's four more examples, and you'll see there's a ton of them when you start doing the conceptual questions for chapter 27. You're going to run into this a lot. I just wanted to make sure you guys had plenty of examples to work with. You can also do things like if you considered a wire loop like this, okay, and current was going around it this way, and we're imagining, for instance, that back part, the left part, is actually behind the page and the right part is in front of the page, then what you can do is imagine grabbing this with your right hand so that your thumb points right along this part. So there's my thumb right there. And now you can see my knuckles of my hand, and my fingers are going to curl around like this. And hopefully that looks enough like a hand for you guys to know what I'm talking about. And that tells you that the magnetic field lines go behind the hand, and then stick out this way. And notice each of those are going in front of that left wire because that left wire is behind the page, and behind that right wire because that right wire is in front of the page. And it goes even behind my hand too. Anybody have any questions with that? All right, so hopefully that helps you a little bit. Now we're going to move on to some specific examples. Your book has figure 2711, and it has a wire going right between the two poles of a horseshoe magnet. That's a case where I was telling you, hey, as soon as you see that figure, you need to cover it up and try to guess the direction of the force in each case, and then move your hand and see if you got it right. You want to do this every darn time, okay? That's the only way you're going to learn how to do this stuff. Now, I've told you that our forces are dF is equal to IDL cross B. If you're lucky enough to have a wire that's whole length is within the magnetic field and doesn't change directions relative to the magnetic field, and the current doesn't change magnitudes anywhere along the wire, and the magnetic field doesn't change directions or magnitude anywhere along the wire, then this can become F is equal to IL cross B, which magnitude wise is the same as ILB sine theta, where IL can be thought of as a vector and the magnetic field can be thought of as a vector. And if you put them tail to tail, then theta would be the small angle between them. Okay, so that's the way that works. That's the way all cross products work as well. So just want to make sure you know that. That's the extension of it not changing. When it doesn't change, you don't have to use the differential dF equals IDL cross B. You can just use F equals IL cross B. And a lot of people write that as BIL because then it makes a word, which is a word I'm fond of. It's more or less my first name, except I have a Y on the end. But anyways, now that we have that, let's do some simple calculations like example 27.1. Example 27.1 says a wire carrying a 30 amp current has a length L equals 12 centimeters between the pole faces of a magnet. The wire is at an angle of theta equals 60 degrees to the field. The magnetic field is approximately 0.90 Tesla. We ignore the field beyond the pole pieces, determine the magnitude and direction of the force on the wire. So what we're given is I is equal to 30.0 amps, and I just added that extra zero with a bar under it, so we know that two of those sig figs are two of those digits are sig figs, and that third one's not. The length of the wire is going to be 12 centimeters, which I'm going to go ahead and write as 0.12 meters, and the magnetic field B is equal to 0.90 Tesla. We've got that. We've also got theta equals 60.0 degrees. Again, making sure we have two sig figs. And we want to know the magnitude and direction of the force on the wire. So we want to know F equals question mark. Let me draw the wire real quick. This is the wire. This is the current. Now here's the magnetic field. And we're assuming that this magnetic field is uniform and has a strength of 0.90 Tesla, what we can see is that the vector IDL, or IL in this case, is actually this vector, because this is the part where we're talking about the length being 12 centimeters. So this is IL vector. And you can also see that the B vector is this one. And we see that this angle is 60 degrees, like that. And we see that we can basically move that B vector so that it's at the tail of the IL vector. And then you see that the two vectors are tail to tail. So that theta equals 60 degrees is exactly the theta we're supposed to use. So F is equal to, in magnitude, BIL sine theta, which for this case is 0.90 Tesla times 30.0 amps times 0.12 meters times the sine of 60.0 degrees. So if we go ahead and calculate all that, we get zero point 0.9 times 30 times 0.12 times sine 60, and that gives me 2.80 point 8, actually 805, so I'm going to call that 2.81 newtons is the magnitude of the force. Now the direction is given by the right-hand rule. Can someone please guess what the direction of this force is? Remember, it's IL, which points up and to the right, cross B, which points to the right. I'm going to work it out. You work it out, and then I'm going. Oh, thank you, thank you for for my drawing compliment. Uh, so using this, right? So I'm going to take my first vector, which is IL, and that's my index finger. I'm going to lay that parallel to the wire. So I see that. And then I got to turn my hand so that my middle finger can point in the direction of the magnetic field. So this is what I should be laying it on the page with. And when I do that, I see my thumb is pointing into the page. So the direction is into the page. Again, you guys should be trying to work this out every time you're encountered with it. Encounter a magnetic field, a current, and you should immediately think of what the force is. Or if you just encounter a current, you should immediately try to think what direction the magnetic field is at various places around the current. So we've got that one. Your book came up with 2.8, the same thing I got, so that's good. Now we're going to look at example 27.2, which is kind of fun. Example 27.2, basically we have a current carrying wire that's hanging uh, from a scale, and the scale has been zeroed out so that it reads zero when there's no magnetic field. However, when there is a magnetic field, then that magnetic field has the ability to change the actual force tugging on the wire. It can actually maybe pull it harder downward, or it might lift up on it. In this case, we've actually designed it, I think, to pull down. But this loop of wire here that we're looking at, this length is supposed to be 10 centimeters. So this is 10.0 centimeters from here to here. And then what we have is a magnetic field in which this thing is immersed, at least from part of it downward. And the fact that I'm drawing circles with dots in the middle means that the magnetic field is coming out of the page. If I drew circles with X's on it, that means it's going into the page. So first off, what I want to do is see if you can tell me what direction is the force on this part of the wire. So that black part I just showed you, what direction is the force on that wire due to the magnetic field? Now, I've drawn a battery on that wire, so you should be able to tell from that that the current is going this way. Okay. So just focusing on that part of the wire that I highlighted in black there, which direction is the force on that portion of the wire? To the left, to the right, in the page, out of the page, up or down? Okay. So this is a QV cross B is one way of thinking about it because you can picture the current as positive charges moving downward in that particular black portion of the wire. Or you can do it as IL cross B because I times L for that black particular part of the wire is pointing down just like QV is. Then you just want to use this right hand rule here. So your index finger is either IL or it's QV, and your middle finger is B. So uh, the page, I'm picturing the page sitting right here. So if I want to take my QL or my IL or my QV, my index finger has to point this way, right? And that means I can turn my hand all these different ways. They're all fine until I get to the point where my middle finger points in the direction of the magnetic field. That happens like this. Now my middle finger's pointing up, but it was really a bad choice of directions for everything because that's going to pretty much ruin my shoulder. But anyways, we're doing like this, and yeah, I know today's not Monday, but I wore the shirt yesterday, and today I didn't have to go in. So, anyways, now I have the magnetic field, my middle finger pointing out of the page. I've got my index finger pointing down the page, and when I do that, my thumb is now pointing to the left. So the force on this side is to the left. Now, if I look at this side, can anybody tell me what direction the force is on that particular side? So I just drew green on there. Now everybody work out the direction of the force on that particular part of the wire. The answers are right, left, in the page, out of the page, up the page, or down the page. Still not getting any answers. Can you all hear me? Anybody not hear me? Ah, yeah, did you hear me? Okay, so for this one, the magnetic field is going up the page, so I hold it like this. Or excuse me, the IL or the QV is heading up the page, so I hold it like this. But then I have to nail my middle finger pointing in the direction of magnetic field, which is out of the page, so that gets me like that. Now I see my thumb is pointing to my right, and that means the force on this portion of the wire, oops, the force on this portion of the wire is to the right. And notice it's the same current going through it. It's the same length of wire and it's the same magnetic field. So those two forces completely cancel out. That was the key to what I saw. What I was trying to work out here. I just needed to figure out whether or not that vertical portion of the wire on the left and that vertical portion of wire on the right, if they're actually contributing. We see that they're not because they're equal in magnitude but opposite in direction, so they're canceling each other out. Now I got to figure out what direction the current in the bottom part of the wire is. So the bottom part of the wire has the current going to the right. Can anybody tell me which direction the force will be in that part? IL or QV? Yes, very good, Alex. IL or QV is my index finger, B is my middle finger, and my thumb is the direction of the force. If I point my finger to the right, which is the direction of the current, and I pick my middle finger to point out of the page, then I see that my right thumb is pointing down. So lo and behold, the force here is in the downward direction, and I should have written that in purple, say. So there's the force for this part, and that's what they're wanting me to calculate. What we are told, though, with this one is figure example 27.2, a rectangular loop of wire hangs vertically as shown in figure 27.14. A magnetic field B is directed horizontally perpendicular to the plane of the loop and points out of the page as represented by the circles with a dot in the middle. The magnetic field is very nearly uniform along the horizontal portion of the wire AB. Where'd I go? I saw AB and then I just lost it. Where did AB go? I really can't see it now. What the heck? Oh, there it is. Okay. It was right next to parentheses. So the magnetic field B is very nearly uniform along the horizontal portion of the wire AB, length L equals 10 centimeters, which is near the center of the gap of a large magnet producing field. The top portion of the wire loop is out of the field. The loop hangs from a balance and reads 0 when B equals 0, which measures the downward magnetic force of 3.48 times 10 to the negative second newtons. So we've got F is equal to 3.48 times 10 to the negative 2 newtons. We've got L is equal to 10.0 centimeters, which is 0.100 meters. And we've got the current I is 0.245 amps. Sorry for that bad writing, but that's 245 amps. And what we want to know is the magnitude of the magnetic field. And actually, I didn't even need to draw the vector up there. I should just wrote it as B. So I want to know the magnitude of the magnetic field. The formula we're using here is all of this is uniform and the directions are not changing, so I don't have to do any differential stuff. What I know is F is equal to IL cross B, which magnitude wise just becomes F equals ILB sine theta. But theta is the angle between IL and the magnetic field. IL is to the right. Magnetic field is out of the page. The angle between them, therefore, is 90. So I've got 3.48 times 10 to the negative 2 newtons is equal to 0.245 amps times 0.100 meters times B times the sine of 90.0 degrees. And of course, the sine of 90 is just 1. So we finally get that B is equal to 3.48 times 10 to the negative 2 newtons divided by 0.0245. That's one extra sig fig there, because I should have 3 sig figs, and this is amp meters in the bottom. So 3.48 times 10 to the negative 2 divided by gives me 1.42, and everything had 3 sig figs, so I'm going to call this 1.420 with a 0 under it, and that is Tesla for the magnitude of the magnetic field. Anyone have any questions on that? Okay. Now it's time for probably the hardest of the problems here, and I'm doing this sort of like the example, but I'm going to do it a little bit differently. This is another example. I'm just going to call this an example because I'm changing some of the details about it, and it's just, I think you'll find it more helpful doing it this way. But this is example like 27.3. So what I'm going to do is I'm going to have a magnetic field that sticks into the page and is uniform. And notice it's sticking into the page because we see the X's. I sometimes choose to put circles around these X's, and that's fine too, but you really don't have to. As long as you've got an X there, that shows everybody that it's the way I have it. What I'm now going to do is show you the wires. So I have a wire coming up basically right here, and I have another wire coming up basically right here. And then I have a half circle going around from one wire to the other so that this is one continuous wire. Obviously, the wire is a distance 2r apart, where r is the actual radius of the circle. So to specify that, I'm going to break off from the straight part of the wire and go ahead and put a coordinate system there to help us. So there's my x-axis. There's my y-axis. And by the right-hand rule, remember your coordinates, your three-dimensional coordinate systems are fine long as they're two-dimensional. But once you put the third, you have no choice in put where you put that third once you've drawn the first two, because it has to be a right-handed coordinate system. So in this case, the z-axis has to point out of the page, and the magnetic field, of course, points into the page. So that's a key thing. This distance right here is the radius. And just like we did before, we can actually imagine the magnetic field due to this portion of the wire and the magnetic field, excuse me, not due to, the magnetic field on this portion of the wire and this other portion of the wire are going to cause forces. We're actually imagining the current going in the upward direction on the left, and then, actually, no, I'm going to go in the upward direction on the right, not the left. So my current is going that way, that way, that way, and then this way. And you can tell that the magnetic field on the little red part to the right, IDL is up, magnetic field is into the page. So the force on this side is this way, and the force on this side is this way. So those two are going to cancel each other out. They're equal but opposite, because, and they're equal because they're the same magnetic field, same current, same length of wire. What doesn't happen is this part in around the arc doesn't cancel out, and what we're going to use is F equals the integral of dF, which equals the integral of I dl cross B. Now, we're going to imagine this little segment right here as being my DL. So my DL is going to be R d theta, because this angle is theta, and then that change in angle from one piece of this one edge of the pie to the other edge of the pie, that change in angle is d theta. And of course that points in the increasing theta hat direction, which I took time to show you already. So I can call this r d theta theta hat. That's the actual direction of the magnet of the DL. The magnetic field B is actually negative B times K hat, because as I told you, when I choose the X to the right and the Y up, that means the Z has to come out of the page, but this magnetic field goes into the page. So now I can go about computing this as follows. So F is equal to, pulling the integral out in front, I get the integral of dl cross B. And of course, that becomes the integral of r d theta theta hat cross negative b k hat, like that. And this is a fine time for us to make use of what theta hat actually is. So I'm going to do that. I'm first going to realize that the r and the negative b, just like the I, can come out in front. So now I'm going to have b times I times r times the integral d theta, and then all we have is the integral d theta times theta hat cross k hat. To work that out, I've still got BIR integral d theta, but theta hat, remember, is negative sine theta I hat plus cosine theta j hat. And I'm crossing that. Oh, the negative came out in front too from the B, so let me put that there too. So remember, it was negative BK, so I pulled that negative out in front. And then this is just taking a cross product with K. So now I've got negative B times I times R times the integral d theta, and now I can basically put the sine theta, which is a negative as well. That's going to make this become a positive BIR, and then sine theta times I hat cross k hat. I hat cross k hat basically is negative j hat, so that's negative j hat. You can work that out yourself with your own right hand rule. And then I'm going to say I had the negative BIR, so I'm going to write negative BIR. And then for the other one, I've got d theta. And then it's going to be, actually, let me put that on the next line because it's clear. I don't have enough space there. So I'm going to say minus BIR. Now this time, this was the cosine one, so I've got the integral cosine theta d theta times now j hat cross k hat, and j hat cross k hat is actually I hat. So that's j hat cross k hat is I hat. Again, you can work that out yourself, but now our job is to go ahead and finish out this integral. So I'm going to get positive b times I times r times the integral of sine theta d theta from theta equals 0 to pi. And then I'm going to have minus b times I times r times the integral from theta equals 0 to pi of cosine theta d theta. And in this case, I get b times I times r. The derivative of cosine is sine, so the integral of sine is negative cosine, or excuse me, the derivative of cosine is negative sine, so the integral of sine is negative cosine. So this is going to be negative cosine pi minus negative cosine 0. Oh, and all that's supposed to come out with the vector symbol, which we got was j hat. I left that off. And the other one was I hat, and I'd left that off as well. So this is the j hat right here. And then minus BIR. The derivative of sine is cosine, so the integral of cosine is sine. So this is going to be the sine of pi minus the sine of 0, and then all of that times I hat. Of course, the sine of pi is 0, and the sine of 0 is 0, so we get nothing there. And symmetry would have told us the I component, the I hat component should have canceled out. In this case, I get BIR times negative 1 minus negative, cosine pi is negative of negative 1. So this would be negative of negative 1 minus, and then the cosine of 0, I know I wrote that as a theta. That wasn't supposed to be a theta. That was supposed to be a 0. The cosine of 0, of course, is 1. So this is minus negative of 1. So in this case, it seems I'm getting I'm getting 1 plus 1, which is 2, and all of that times j hat. So finally, I get 2BIR j hat is the total force acting on this, and that's it. You guys are free to go. I will hit the rest of these examples next time really quickly, or I might just make a quick video with there's only like 3 more examples I wanted to do, and we'll be finished with all of chapter 27. So I might make a little video, send that to you, or I might just wait and cover it next time. Uh, you are all free to go. Make sure you chat me your first and last name. It isn't supposed to be negative. In this case because I ended up getting a negative of cosine pi, which cosine of pi is negative 1, so a negative of negative 1 is positive 1, and then minus the negative cosine of 0, and of course the cosine of 0 is 1, so minus a negative is a positive, so it's 1 plus 1, and this comes up to 2 BIR. The book example, I think it also came up with the same result. In fact, it did. It got 2 BIR, only their current went the opposite way. So that leads me to think that it should have been a negative. So yeah, check for my sign errors. I might have made one in there, but all the physics and math is right. I just might have dropped the sign. Well, I shouldn't say the math is right if I drop the sign. Any questions on that, Alex?
Oh, I think it's all good. And I think I see the sign. It's on the whenever you wrote plus BIR
Uh-huh.
integral d theta sine theta negative j hat. I think that's where
That's where I dropped the negative.
yeah.
Yeah, good job. Nice catch. And that'll be on this recording, so that's super helpful too. But I'll say right here, I'll put a big note on it so everybody will know I dropped
But I do have a
this.
question
Yes.
about when you were trying to explain the electric field and you had the four dots around the black dot.
Mm-hmm.
So you were trying to explain the electric field acting on that dot, correct?
Yes, the magnetic field at that dot, not acting
At
above.
that
Yeah,
dot.
at that dot.
Okay.
Which I don't know there's really any difference of acting on that dot versus at that dot. I just didn't want you to think that it was in some sense uh, a force or anything like that. That's the weird thing about
Okay.
a magnetic field. It exists, but the force is a whole separate step that you got to go through.
That makes more sense. Thank you.
Okay, no problem. Is that all you needed, Alex?
I believe so. Cool.
All right. Well, have a good one. I hope you enjoyed this example and followed it somewhat. That's like the only hard thing about this entire chapter is this one example. The rest of them are pretty straightforward, but do practice with those right-hand rules as often as you can, as I told the other students to do.
All right. Well, I hope you have a great day.
You too. See you, Alex. Have a good one. And that's it. So yeah, I was off by a negative, so I've corrected that by writing where it was went wrong, and then I corrected it all by putting the red on there. So we ended up getting negative 2 BIR J hat, and that is correct. So thanks for coming, everyone. Bye bye.